The Hubble telescope is one of the best inventions of our century, which has been contributing to other discoveries as well. However, the latest news regarding the Hubble telescope has something else to say. But what is this news about? How did the Hubble telescope break physics? And who was behind the Hubble? Continue watching the video till the end to know more. Hey everyone, and welcome back to yet another video from our channel. We hope you guys are doing extremely well. In this video, we will be talking about the Hubble telescope and how it proved that physics is broken. We will be diving deep into every aspect of this news, so if you are new to this channel, then make sure to hit the subscribe button. Now, without any further ado, let's hop right into the video. Something weird is going on with how our universe is expanding, and it cannot be explained by current physics, NASA has revealed. Data from the Hubble Space Telescope has shown there is a huge discrepancy between the universe's current rate of expansion compared to the rate right after the Big Bang. The iconic orbital observatory has just completed a 30-year marathon of data collection. With this information, Hubble was then able to identify more than 40 milepost markers of space and time to help scientists more accurately measure the expansion rate of the universe. However, the more precise these measures become, the more they indicate that something weird is happening, the U.S. Space Agency said. The cause of this discrepancy remains a mystery, but Hubble data, encompassing a variety of cosmic objects that serve as distance markers, support the idea that something weird is going on, possibly involving brand new physics, NASA officials said. Experts have been studying the universe's expansion rate since the 1920s using measurements by astronomers Edwin P. Hubble and George Lemaitre. When NASA conceived of a large space telescope in the 1970s, one of the primary justifications for the expense and extraordinary technical effort was to be able to resolve Cepheids, stars that brighten and dim periodically, seen inside our Milky Way and external galaxies. Cepheids have long been the gold standard of cosmic mile markers since their utility was discovered by astronomer Henrietta Swan-Leavitt in 1912. To calculate much greater distances, astronomers use exploding stars called Type Ia supernova. Combined, these objects built a cosmic distance ladder across the universe and are essential to measuring the expansion rate of the universe, called the Hubble constant after Edwin Hubble. That value is critical to estimating the age of the universe and provides a basic test of our understanding of the universe. It can be used to predict how fast an astronomical object at a known distance is moving away from Earth, although the true value of the Hubble constant remains up for debate. Almost 25 years ago, astronomers also discovered dark energy, which NASA describes as a mysterious repulsive force accelerating the universe's expansion. The new research by the Hubble Space Telescope measured 42 of the supernova mileposts, more than double the previous sample of cosmic distance markers. However, when it started gathering information about the universe's expansion, a discrepancy emerged. Hubble's measurements suggest the rate is roughly 45 miles, 73 kilometers, per megaparsec. But when taking into account observations of the deep universe, this slows down to about 42 miles, 67.5 kilometers, per megaparsec. A megaparsec is a measurement of distance equal to 1 million parsecs, or 3.26 million light-years. This suggests that the universe's evolution and expansion is more complicated than we had realized, and that there is more to learn about how the universe is changing. NASA said astronomers are at a loss to figure out why there are two different values, but suggested we may have to rethink basic physics. You are getting the most precise measure of the expansion rate for the universe from the gold standard of telescopes and cosmic mile markers, said Nobel laureate Adam Rees of the Space Telescope Science Institute, SDSI, and the Johns Hopkins University in Baltimore, Maryland. He leads a scientific collaboration investigating the universe's expansion rate called SHU-ES, which stands for supernova, H0, for the equation of state of dark energy. This is what the Hubble Space Telescope was built to do, using the best techniques we know to do it, Rees said. This is likely Hubble's magnum opus, because it would take another 30 years of Hubble's life to even double this sample size. Rees said it was best to see the expansion rate not for its exact value at its time, but its implications. I don't care what the expansion value is specifically, but I like to use it to learn about the universe, he added. NASA now hopes to gain more clarity about the expansion of the universe with the help of the James Webb Space Telescope, launched in December last year. It should allow scientists to see new mileposts that are even farther away and in better resolution. The DIAC REPANCLI B2E in how fast the universe seems to be expanding and how fast we expect it to expand is one of cosmology's most stubbornly persistent anomalies. Cosmologists base their expectation of the expansion rate, a rate known as the Hubble constant, on measurements of radiation emitted shortly after the Big Bang. This radiation reveals the precise ingredients of the early universe. Cosmologists plug the ingredients into their model of cosmic evolution and run the model forward to see how quickly space should be expanding today. The discrepancy, known as the Hubble tension, has persisted even as all the measurements have grown more precise. Some astrophysicists continue to debate whether the tension might be nothing more than a measurement error. But if the discrepancy is real, it means something is missing from cosmologists' model of the universe. Recently, theorists have been busy imagining new cosmic ingredients that, when added to the standard model, would rev up the universe's expected expansion rate, making it match observations. Discovering anomalies is the fundamental way that science makes progress, said Avi Loeb, a cosmologist at Harvard University and one of dozens of researchers who have proposed solutions to the Hubble tension. These are some of the top ideas for what could be speeding up cosmic expansion. The standard model of cosmology incorporates all the familiar forms of matter and radiation and their interactions. It also includes the invisible substances known as dark energy and dark matter, which together make up some 96% of the cosmos. Because so little is known about these dark ingredients, they are perhaps the obvious place to begin tampering with the standard model. That's what you have at your disposal to change the expansion rate of the universe, Loeb said. The standard model assumes that dark matter consists of slow-moving particles that don't interact with light. But what if we also assume that dark matter is not made of just a single substance? Since many different kinds of visible particles exist, quarks, electrons, and so on, there might be multiple dark particles as well. In a paper published last summer in Physical Review D, Loeb and two collaborators considered a form of dark matter that decays into a lighter particle and a massless particle known as a dark photon. As more and more dark matter decayed over time, they reasoned its gravitational pull would have lessened, and thus the expansion of the universe would have sped up, relieving the Hubble tension. But making small changes like this to the standard cosmological model can have unwanted knock-on effects. It's very easy to come up with all kinds of slight modifications, said Mark Kamiankowski, a theoretical physicist at Johns Hopkins University, but it's hard to do so, he said, without ruining the model's perfect fit with a wealth of other astronomical observations. By varying the decay rate and the amount of dark matter that is lost in each decay, Loeb and colleagues selected a model of decaying dark matter that they say still agrees with other astronomical observations. If you add this ingredient to the standard model of cosmology, everything holds together, Loeb said. Yet he remains dissatisfied with the decaying dark matter idea, in part because it introduces two new uncertain quantities into the equations. In this case, you add two free parameters in order to resolve one discrepancy. And I'm uneasy about that, he said, comparing decaying dark matter to the epicycles in Ptolemy's Earth-centric model of the universe. I would rather have two discrepancies explained by one parameter. The only life we know of is right here at home. For the moment, we're staring into the void, hoping someone is staring back. And that's all for today. Did we miss out on anything? Do you have any other insights on this news? Did you enjoy watching the video? Let us know your thoughts in the comments section down below. Well, that brings us to the end of this video. We hope you have enjoyed watching the video. Please like the video if you have not already and make sure to hit the subscribe button. Don't forget to press the bell icon to never miss another update from our channel. With that being said, let's meet in another one of these videos. Until then, see ya!